Welcome back to linear algebra. There's no Anki flashcards due today, but I am gonna just open a flashcard because I don't want to kill my streak because I don't have anything due. All right, streak is alive. What did we learn about yesterday? Okay, we're into 1.6. This is on more linear systems and matrix inverses. Essentially, I think it revolves largely around the idea that you can solve a linear system using a matrix inverse as long as the matrix is invertible, which means it's a square that's invertible, square matrix. You can solve it using AX equals B. That's the matrix, that's linear system, A being the coefficient matrix that is invertible. Then you can solve it basically by multiplying both sides by the inverse, aka X. The solution set equals the inverse of A times B. B being, what would B be? 0? No, B. What the heck? So I guess B would be the constants. So there's three ways that we've learned how to solve linear systems: Gauss-Jordan, Gaussian elimination, Gauss-Jordan elimination, Gaussian elimination, and then matrix inverse. We also learned yesterday how to solve multiple linear systems at the same time as long as they have the same coefficient matrix. You basically throw the coefficient matrix in there, you partition a bunch of the B's in a row, and then you solve using Gauss-Jordan elimination row by row, and you apply all the things you apply, the things you apply to the matrix, coefficient matrix, you apply to the B's as well. Matrix doesn't even have to be invertible for that to work, so that's cool. That's a great way to solve a bunch of them at the same time. And then the beginning of the chapter, we learned about it was basically a proof for why why a linear system has 0, 1, or infinitely many solutions. I think that's that, I think. The proof basically showed, I'm not gonna run through the whole thing. The proof basically showed that if there's more than one solution, there has to be infinitely many solutions. All right. If the matrix is invertible, there's exactly one solution. Interesting. I forgot that, I guess. All right. So I'm going to continue reading and learning more, and I'll be back to recall what I learned a little bit. All right, so what did we learn today? Something we learned was that there's an expansion of equivalence theorem. So the equivalence theorem from the previous chapter stated that if we know one of these, we can know all of them. A matrix is invertible. The equation AX equals 0 only has the trivial solution. The reduced row echelon form of A is the identity matrix. And what was the last part of it? I don't remember what the fourth part. We learned two more additions though. The equation AX equals B is consistent for all row vectors B that are n by 1 row vectors. It's consistent for all of them, and it has exactly one solution for all those different row vectors. Those are the other two additions to equivalence theorem. What else we have learned? There's something. If we know that A times B equals I, well, then we know B times A equals I as well. So we only need to know one to know both. Therefore, both of them are there. If we know A times B equals I, or if we know B times A equals I, then we know that they're inverses of each other. If we know, or we know that a product of matrices, the resulting matrix of a multiplication, like the product matrix, if that's invertible, then we know the factors are invertible as well. We're just starting to talk about this or read about this thing called fundamental problem, or a fundamental problem. So more on that tomorrow. The fourth thing was A is expressible as a product of, or a sequence of a product of elementary matrices. If A and B are square matrices and the same size, okay, so if we know, so if we know that, if A and B are square matrices of the same size and their product is invertible, then the factors are invertible. That's how we know, okay? Okay, that was everything from today. So we'll probably have one more day of reading 1.6, and then we'll be into practice problems. So that's it for today. Talk to you tomorrow. See you.